This video focuses on Euler's method. Before we talk about Euler's method we kind of need to see the bigger picture, so we're going to take a step back and think about what we can do with tangent lines. And one of those things is we can approximate functions using a tangent line. So I have my function, this black one right there, and my tangent line, the red line, is tangent at this point. So I know that at that point the tangent line and the function are the same. But at all of the other points, the tangent line is probably different from the function. I mean, it could cross it again, maybe, but it doesn't have to. So it's only definitely the same at this one particular point. But if we look at the points close to that tangent point, then we see our function and our tangent line are not so different from each other. So if we're trying to approximate something that's pretty close to our tangent point, then we can use the value that's on our tangent line, and that'll be pretty close to the actual value of the function. So for instance, if my tangent is at point x equals a, and then my delta x is relatively small, then a plus delta x, this would be my approximate y value, and that's my actual y value, the one on the function. And you can see like this distance between them is not too big, but if I had like a giant delta x, and so I'm over here somewhere, the distance between the tangent line and the function line is huge, so that's not a really good approximation. So we can use tangent lines if delta x is really small. So of course the question is, well, what if delta x isn't really small? Or what if we want a better approximation, even if delta x is small? So what we have to do is bend our tangent line, basically, or we're not using a tangent line anymore, but we're starting at the tangent line. So as we move in the x direction, as we add a delta x in there, we also need to move in the y direction and add in a delta y. And here's what that actually looks like. So we still have the same function, we still have our same tangent line that's tangent at point x equals a, and we start with this, so our delta x, we move over to here, but then instead of using that as our approximation, we figure out what our delta y should be, and now this is our approximation, so it's a lot, I didn't point exactly to it, but that's our approximation, and it's a lot closer to the actual value than what we had before. So the next question is, well, how do we figure out what our delta y should be? But we already know a couple of things that help us figure that out. So we know the equation for our tangent line, which means we know the slope of our tangent line, which is dy dx. And then the other thing that we know is delta x. We know how far we want to move in the x direction. So if I multiply these two things together, and if delta x is small enough, it's basically the same thing as dx. So these two cancel each other out, which leaves us with dy, which is pretty much the same thing as delta y when we're looking at situations this small. So big picture, Euler's method is a way to approximate the value of a function, or you can also think of it as a way to approximate an answer for a differential equation giving an initial value. So here's an example. There are different ways that they could phrase this. They could say approximate the value of the function given that dy dx is equal to 4x and y of 1 equals 3. They could also say solve the initial value problem. So we have to estimate y of 2 with a step size of 0.5. Alright, so there's a lot going on in this chart, but this is the chart that you're going to reproduce every time you do one of these problems. So the headings are the important things right here. This is the stuff that we should know. Every time we do Euler's method, we're going to use those columns. Alright, so they told us an x, they told us a y, so those are my first columns, x and y, and they also told me what dx is, or dy dx. So dy dx, you don't have to write the function here, I just did that to make it a little bit easier to follow what I'm doing. And then we also know what delta x is, because delta x is how far we're moving every time in the x direction, so we're moving 0.5 every time in the x direction. And then everything else, delta y, new x, new y, we have to figure that out from the stuff that's in our table. So we start by filling out our table. Originally x is equal to 1 and y is equal to 3. And that's all I know, aside from dy dx is 4x, but I know that x is equal to 1. So I'm going to do 4 times 1 equals 4. And then the next thing I know is delta x, so delta x is 0.5. And now if I remember from my previous slide, dy dx times delta x is what gives me delta y. So I'm going to take these two columns, right here, 4 and 0.5, and multiply them together. 4 times 0.5 is equal to 2. The next thing I need to figure out, well, where's my new x? Because I started at an x, and then I moved delta x. So I started at 1, and then I moved over 0.5, so my new x is 1.5. And then I also need to know what is my new y. So I started with this y, and then I moved I moved up delta y. So I started at 3, and then I moved up 2, which means my new y is 5. So this is a good point to remind yourself, what x are you trying to get to? And we're trying to approximate the function at x equals 2, because that's what they told us. So I need to go one more step, because right now I'm only at 1.5. So I come over here, and now my x is 1.5, because that's what I had, that's my new x, and then my new y is 5, so I put 5 down here, and I go through this process again. So dy dx is still 4 times x, and this time my x is 1.5, because that's what's here. 4 times 1.5 is 6. My delta x is still 0.5, because my step size does not change. And then to find delta y, I do dy dx times delta x, and that gives me 3. So my new x, I had 1.5, and then I stepped over 0.5, so that would give me 2, which is what I was looking for. And then my new y, I was at 5, right here, and then I moved up 3, because that's my delta y. So my old y plus my delta y gives me my new y, which is 8. So another way to think about this, when x is equal to 2, our approximate value says that y is around 8, and it's pretty close to it. Alright, so go ahead and try this problem. It's the same basic layout. I give you dy dx, and I tell you that the initial value at x equals 1, y is equal to 0. We're using a different step size now, 0.25, to approximate the value of f of 2. Go ahead and try it, pause the video now, and when you are ready, unpause the video and we'll look at the solution together. So here's my table. I'm not going to go through all of the numbers, but basically you should have 4 different x's. There's the one that you start with, and then after 1 step, after 2 steps, and after 3 steps. And then here's the very last one. This is after 4 steps. The approximated value for this would be 0.75, so that's what we're looking for. And I'll leave this here if you want to pause it for a second and check your numbers. Now, here's the same problem, but solved with an integral so that we can actually see what the exact value is, and we can compare that to our approximate value that we just found. So I get dy dx is 2 times x minus 1, which is what we had on the last slide. We can turn this into a separable differential equation. So I move all my x's to one side, y's on the other, take the integral, and I end up with this function right here. You can simplify it if you want to, you don't have to. And then I plug in my initial value, so y is 0 when x is equal to 1. And when I solve that, I find that c is equal to 1. So I go back here, and I have y, this is my particular solution with my value of c plugged in. Now, at x equals 2, this is what we were trying to approximate before on the last problem. So I'm going to just plug in 2 for x. And when I simplify that, I get y equals 1, which is pretty close to our approximated value of 0.75. And that is the end of this video. Please ask if you have questions.